Let's talk about the chain rule. The chain rule is one of the most complicated differentiation rules, but it is also one of the most useful ones. The key point to understand about the chain rule is that the chain rule helps us make substitutions in formulas containing derivatives of functions. Let's briefly review how we make substitutions in formulas that do not contain derivatives of functions, and then I will explain the chain rule and how it helps us to make substitutions in formulas that do contain derivatives of functions. Let's consider, for example, the familiar equality a plus b squared equals a squared plus 2ab plus b squared. This equality is an identity. What this means is that this equality holds regardless of what the values of a and b are. We can substitute instead of a and b arbitrary numeric values, and the result will be correct equality. For example, if we substitute instead of a 2 and instead of b 3, then on the left hand side we will get 2 plus 3 squared, which is 5 squared, 25. And on the right hand side we will get 2 squared plus 2 times 2 times 3 plus 3 squared. And it's easy to check that that actually adds up to 25 as well. Now, note also that we can substitute instead of a and b not only numeric values, we can substitute expressions containing the same variables, a and b, or some other variables. So for instance, we can replace a with x squared and b with, let's say, 1, and that's going to give us the following identity: x squared plus 1 squared equals x squared squared plus 2 times x squared times 1 plus 1 squared. And we can further simplify this to x to the 4th plus 2x squared plus 1. And so if one, for example, needs to differentiate or integrate x squared plus 1 squared, then one can replace that expression with an equivalent expression, x to the 4th plus 2x squared plus 1, and then differentiate or integrate term by term. Now what I want to draw your attention to here is that the substitution process is extremely simple here. We simply replace each letter, a and b, with whatever we want to replace them with on both sides of this identity. And we don't really need to do anything else. Let's see if the same approach will work for equations containing derivatives of functions. So let's start, for instance, with the derivative of x squared. You probably know that by the power rule, the derivative of x squared equals to 2x. Now suppose now we want to substitute or replace x with x squared. Let's try to do this in the exact same way as we performed the substitution in an algebraic identity explained earlier. Then replacing x with x squared on both sides gives us the following equality: the derivative of x squared squared equals 2 times x squared. What I did here is everywhere we see x on the left hand side and on the right hand side of this equality, I simply replaced it with x squared. Now this formula now simplifies to say that the derivative of x to the power 4th equals 4x equals to 2x squared, sorry. And unfortunately, perhaps somewhat surprisingly, this is not correct any longer. So this is not correct, because by the same power rule, the derivative of x to the power of 4 is equal to 4x cubed. I almost made a mistake by saying that the derivative of x to the power of 4 is 4x cubed in this result, because the derivative of x to the power of 4 is 4x cubed. So what the chain rule does, it tells us how to correct this incorrect result when making a substitution in the formula for a derivative. What the chain rule says is that if we're starting with the formula for containing a derivative of a function which is correct, such as x squared prime equals to 2x, and suppose we want to make a substitution, such as replacing x with x squared, then in order to end up with the correct result for the derivative, we need to go ahead and do our substitution in the same way as we are used to, replacing x with whatever we want to replace it with on both sides of the equality. But then the right-hand side of the equation, assuming that the left-hand side is the derivative itself, then on the right-hand side, in addition to replacing x with, in this case, let's say x squared, we need to multiply that right-hand side by the derivative of what we are replacing x with. And so this is how it would look like. Replacing x with x squared gives us the derivative of x squared squared equals 2 times x squared. So far all I did was replacing x with x squared on both sides, but now on the right hand side we need to multiply whatever we obtained by replacing x with x squared. We need to multiply that by the derivative of what we are replacing x with. So in other words, in this particular case, by the derivative of x squared. And so now you see what we get for the derivative of x to the power of 4 is 2x squared times 2x, and that simplifies to the correct result of 4x cubed. Applying the chain rule in practice is a little bit more complicated than what I've just explained. This is because in a typical calculus problem, we are not given a correct formula for the derivative of some function and then asked to make a substitution. Instead, we're given a function and then we need to calculate its derivative by whatever means or rules we think are appropriate to use to accomplish that. In those cases when the chain rule is applicable, we need to realize that the function that we're differentiating can be obtained from a simpler function by means of a substitution. Once we realize that, we can apply the chain rule to calculate the derivative of the function. Let's take a look at the following example, where we need to calculate the derivative of the function y equals to cosine squared x. First, note that in this notation where square appears next to the function cosine means that we're first calculating the cosine of x. So given the x value, we would calculate the cosine of that value, and then we will square that cosine value. By looking at this function, the first thing that you can notice is that the y value is the square of some other number, namely cosine of x. So that actually tells us that our function can be obtained from a simpler function, namely from the function y equals to x squared, by means of a substitution in which we replace x with cosine of x. So if we start with the function y equals to x squared, and then replace x with cosine of x, the result of that is that we get y equals to cosine of x squared. And therefore, the chain rule is can be used here to calculate the derivative of our function. We will start with the derivative of the function x squared. Of course, again, that is 2x. And then we will proceed to make a substitution replacing x with cosine of x in this formula. The first step is to simply replace x on both sides of this equality with cosine of x. This is a fairly easy step, mechanical step, where we simply write cosine of x instead of every x that appears in our formula. And then this is where the chain rule comes in. On the right hand side, we will need to multiply by the derivative of what we are replacing x with, in this particular case with the derivative of cosine of x. Since the derivative of cosine of x is negative sine x, we obtain that the derivative of cosine squared of x is 2 cosine of x times negative sine x. I can move the negative sign in front. We can also interchange cosine and sine x to rewrite this as negative 2 sine x times cosine x. And then you may also know the formula from trigonometry, which says that 2 sine x cosine x is sine of 2x. This is a double angle formula from the trigonometry. So we can actually simplify our final answer as negative sine of 2x. I will also note here that we could have calculated the derivative of this function by using the product rule. Right, so we could also write that cosine x squared is cosine x times cosine x. And then we could calculate the derivative of this function using the product rule. We will obtain exact same result without using the chain rule. Now I would like to explain the general formulas for the chain rule that you may see in your textbook. Let's start with the first version of it that is very close to what I was explaining to you earlier. So remember that the chain rule tells us how to make a substitution in a formula for a derivative of a function. So suppose we start with the function f of x. Right, and suppose we have a formula for the derivative of this function. So what I'm going to write here is going to look trivial, but what I mean here is, for example, that earlier I was explaining the chain rule. We started with the function x squared, and we said that that is 2x. The derivative of x squared is 2x. And so this is what I'm sort of thinking about when I'm writing this. I have a function f of x, and its derivative is some function which is denoted by f prime of x. And now what we want to do is we want to replace x with another function, another expression. And let's call that expression g of x. So in the example that we've just went over, I was replacing x with cosine of x. And so cosine of x was that function g of x, but in principle it could be any function. And so let's look at the formula that we have here, right here, and let's go ahead and replace x with g of x. So first step is mechanical step, where everywhere we see x in this formula, we're going to replace it with g of x. So then on the left hand side, we're going to get f of g of x prime of all of that. So the derivative of this function, and this notation f of g of x indicates that is what we get by replacing x with g of x in a function f of x. On the right hand side, we're going to get f prime of g of x. That is the result of substituting instead of x, g of x into the derivative of f. And then the chain rule says that this right hand side has to be multiplied by the derivative of what we're replacing x with, namely g prime of x. And so this is one version of the chain rule that you will likely see in your textbook. And really, if you wanted to formulate this if you want to read this formula in English, you would phrase this exactly by saying that if you start with a formula, correct formula for a derivative of a function, then, and you want to make a substitution, then the first step is to mechanically replace the variable x or any other variable that you're replacing with whatever you want to replace it with, and then on the right hand side you need to multiply by the derivative of what you're replacing with, x with, or the other variable, the main variable with. And so just like in the example that we've just completed, if I replace x with cosine of x in the formula for the derivative of x squared, then we get the formula for the derivative of cosine squared x. Okay. Now, there is a different version of the chain rule that actually is also very useful, and you may find it easier. So this is going to be chain rule version 2. And so this version uses additional variables, which addresses the following issue that you may have somewhat felt uneasy about. You see, like in this example where we went to calculate the derivative of the function cosine squared x, we started with the function y equals to x squared, and then we substituted instead of x cosine of x. And maybe, I'm not sure if it bothered you at all or not, but we were replacing x with a function of the same variable x. And so in particular, we can't really write x equals to cosine of x because that would be incorrect for most values of x. And in fact, we don't really need to use exact same letter everywhere for like we don't really need to use x everywhere in this example. So here's a different version which you may find a little bit easier to understand. So again, I'm going to start with the function y equals to cosine of x squared. And we're going to introduce another variable, t, and we're going to set t equal to cosine of x. So if we do that, then y becomes equal to t squared. Now really what we accomplished here is the exact same thing than earlier. What we're saying is that y equals to t squared, but t is equal to cosine x. And this is saying exact same thing that we realized earlier, that the function y equals to cosine x squared can be obtained from the square function y equals to t squared or x squared by replacing the variable in that function t or x with the function cosine x. But the advantage of using a different variable, t in this case, is that now I can really write t equals to cosine x, and we can really think of t as being equal to cosine x. In contrast with the previous notation that we were using, we couldn't really say that x equals to cosine x, and I was using that squiggly line to indicate that we're replacing x. We're replacing x with cosine x. I couldn't really say that x equals to cosine x. But if we're using a different letter, now we can actually say that t equals cosine of x. And this version of the chain rule uses a different notation for the derivative, namely the Leibniz notation. And the advantage of using the Leibniz notation is that it actually specifies the variable with respect to which we're differentiating. So what we really need to calculate in this problem is dy dx, the derivative of y with respect to x. When we say that we need to calculate dy dx, we're calculating the derivative. We're saying that we need to calculate the derivative of y as a function of x. And so this is our goal, to calculate dy dx. Now, but what we're saying by introducing intermediate variable t is that our function that our variable y actually depends on the variable t, and the variable t in turn depends on the variable x. And so we can calculate the derivative of y with respect to t. For this derivative, it doesn't really matter how y depends on x. For calculating the derivative of y with respect to t, we only need to look at the relationship between y and t, which is y equals to t squared. And so the derivative of y with respect to t, the derivative of dy dt equals to 2t. Now, the derivative of t with respect to x, right, dt dx, is the derivative of cosine x. Remember, that is the derivative of what we are replacing t with, or in earlier version, in earlier notations, it's the derivative of what we're replacing x with. And so that is the derivative of cosine x, which is negative sine x. And so then the chain rule says that dy dx, the derivative of y with respect to x, equals the derivative of y with respect to t, right? So that's 2t multiplied by the derivative of t with respect to x. So in these notations, we're going to get 2t times negative sine x. Now this looks a little different from what we've got earlier. Earlier we got negative 2 cosine x sine x, but all we have to remember, all we have to do to obtain that result is to remember that t is equal to cosine x, and if we substitute cosine x instead of t in this formula, we're going to recover that result, 2 cosine x times negative sine x once again. Right, and so this is the second version of the chain rule that you will probably see in your textbook. And so the advantages of this form is, first of all, that it emphasizes, for each of the derivatives, it emphasizes the variable with respect to which we're differentiating. That is something that we don't see in the prime notation for the derivative. And the other useful advantage of this formula is that it is easy to remember, because if you imagine for a second that these derivatives, dy dx, dy dt, dt dx, are fractions, then this formula becomes almost trivial, because if these are fractions, then you could cancel out the denominator dt with the numerator dt on the right hand side, and then you have the obviously correct formula dy over dx equals dy over dx. Of course, this cancellation of dt on the right hand side is not completely valid because these derivatives are not fractions, but what the chain rule says is that the derivatives behave a little bit like fractions in this instance. Let us finish by looking at the another example where we need to differentiate the function y equals to tangent cube of 2x. This is a more complicated example of using the chain rule because we will see that to differentiate this function we will have to use the chain rule twice. Begin by clarifying a little bit what this function is. We see the cube next to the tangent, and so tangent is being cubed, but tangent is applied to 2x, and so perhaps a little bit easier to understand way to write this function is to do the following. Tangent of 2x, so for given the value of x, we would multiply that x value by 2, then we would calculate the tangent of 2x, and then the tangent value will have to be cubed. The last operation that is being given, that needs to be completed to calculate the value of y is raising the number to the third power, taking the cube. And so let us introduce an intermediate variable t and set it equal to tangent of 2x. So then we can rewrite our function y in terms of this variable t as simply y equals to t cubed. Therefore, we can easily then calculate the derivative of y with respect to t, because it's simply the derivative of t cubed with respect to t. By the power rule, this derivative is equal to 3t squared. But we're not finished here because this is the derivative of y with respect to t. If you look at the original problem, there was no variable t in that function. We were given the function y equals to tangent cube of 2x. And so when the problem says differentiate that function, it means calculate the derivative of y with respect to x. In other words, what we need to calculate is the derivative dy dx. But this is where we will use the chain rule. And remember that dy dx equals dy dt, which we just calculated, multiplied by the derivative of t with respect to x dt dx. So far what we have is that dy dx equals 3t squared multiplied by dy dx. Now, of course, here I can replace t with tangent of 2x, right? So that's going to be 3 times tangent of 2x squared multiplied by multiplied by dt dx. I've got to carry it away here. So multiplied by dt dx in both places. And so to calculate dy dx, now we need to calculate dt dx. Now t, remembering what t was, we see that t equals tangent of 2x. Now let's think for a second. What steps need to be taken to calculate the value of t given the value of x? Given the value of x, the first thing that we need to do is double that value, multiply x by 2, and once we have that, we need to take tangent of that value. So the last operation that we'll be doing is tangent, and that tangent is going to be applied to 2x. Let's introduce another intermediate variable, namely let 2x equal to u. This simplifies our function because now t, we can now write t as simply tangent of u, right? So you just simply say, okay, well, t is a tangent of some number. Let's denote that number by u. So then we can write tangent t as a tangent of u, and this is a simpler function, the tangent of 2x. We sort of hid our complexity of our function partially in that intermediate variable u, which is equal to 2x. So now, again, we use the chain rule to calculate dt dx. Namely, we can calculate dt dx as dt du times du dx. Now the derivative of t with respect to u is simply the derivative of tangent, and you may know that this derivative is equal to secant squared u. And the derivative of u with respect to x, for that we will look at the formula, which tells us what the relationship is between u and x. U equals to 2x, and the derivative of 2x with respect to x is just 2, so times 2. Here we can substitute instead of u 2x to express dt dx in terms of x. 2 times secant squared of 2x. And this is the formula for dt dx, which we can now plug in into the formula for dy dx that we had earlier. And so putting all of these things together gives us the final result. Dy dx equals 3 tangent squared of 2x multiplied by 2 secant squared of 2x. We can combine 3 and 2. 3 times 2 is 6. And write the final result as 6 tangent squared of 2x times secant squared of 2x. And this is how you can use the chain rule to calculate derivatives of complicated functions.